All right, so we're going to talk about Stoich with gas laws. I wanted to show you a couple of problems that use stoichiometry, and then because it's not at STP, then also use the ideal gas law. So the first one we're going to look at is the combustion of propane. First thing we need to do is balance our chemical equation. So I have 3 carbon in propane, so I'm going to put the coefficient of 3 in front of carbon dioxide. I have 8 hydrogen in our propane, so 8 divided by 2 is going to be 4 in front of water. Then I'm going to add my oxygen on the product side. I have 3 times 2 is 6, plus 4 is 10, divided by 2 gives me 5. So I've balanced my chemical equation. Now let's annotate the balanced chemical equation. What volume of oxygen gas, so question mark liters, at 25 degrees Celsius and 1.04 atmospheres is needed for the complete combustion of 5.53 grams of propane? So 5.53 grams of propane. Well, the big thing here that I want you to see is that this is not at STP. Definitely not at STP. Not at STP. So we can't just use our molar roadmap and go from grams of propane to volume of oxygen at STP, knowing that the volume of any mole of gas at STP is 22.4 liters. So we've got to go from grams to moles of oxygen, take our number of moles of oxygen and put that into the ideal gas law to then figure out how many liters we can produce or that we need. So let's start with our dimensional analysis and our stoichiometry. So we're always going to start with our given. We have 5.53 grams of propane. And because I'm going to go from grams to moles, that'll be 3 boxes. That's kind of what we call it. So we've got moles of propane. And then we're going to go to moles of oxygen. We're going to stop there. So we put a 1 underneath our given, grams of propane, moles of propane. Okay, for every 1 mole of propane, we're going to take the molar mass, so 3 times 12.01 plus 8 times 1.01. I calculated it and I got 44.11 grams molar mass. Then this one is our Stoich step. So we have coefficient of 5 that corresponds to moles of oxygen, and coefficient of 1, that invisible 1 that corresponds to moles of propane. So I'm going to multiply everything on the top divided by everything on the bottom, and I end up with 0.62684 yada 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 moles of oxygen. Well, this equals our N, and we're about to put it into our ideal gas law. So PV equals nRT, and we're going to solve for V. So that means that V equals nRT over P. So we have our N, and that is 0.62684. And yes, I did use a few more digits so that we wouldn't cut off our sig figs and at the end. And if I go back in my equation or my question, I have temperature is 25 degrees Celsius and pressure is 1.04 atmospheres. I'm trying to find volume. The only other thing that's missing is my R. So R, ideal gas law constant, 0.0821 liter atmospheres divided by mole Kelvin. Latim molx. All right, so at this point, what do you see that we need to convert? Well, moles is fine. We need to convert our temperature to Kelvin. So that's going to be 298 Kelvin. Atmospheres is fine. And we're ready to solve. So number of moles, 0.62684 moles times R, 0.0821 liter